All right, everyone, we are back and we are going to work on our second problem in this particular exam. So bend, don't break. So cobalt beam, so metallic beam, length of this, width of this, thickness of this. So I'm going to find my coordinate system, x, y. I'm going to set this as my basically 0 over here. So we have a cantilever beam. So we are going to have, we can write these when we get into the code, but at y of 0, I'm going to have deflection of 0, y prime of 0 equals 0. There is going to be a moment here, so I'm going to have E dot I dot Y double prime at 0 is going to be equal to my moment. So my reaction moment is going to be equal to, so my moment here, so let's see, when it goes, I remember our moment, positive notation essentially here. So it will go up. So my moment will actually go the opposite direction. So some of the moments here, some of the moments at this or at 0 or my origin must be equal to 0 equals, and it will be actually a minus, equals minus m. But that just means that then it'll be minus 30 newtons times L over 5 plus 2 times 10 to the 3 newtons times 5L over 6. That's going to be solved for my moment, then that's going to be substituted in here because this is just effectively equal to my moment. So we'll get that value. And then over here, we know that y double prime at L must be equal to 0. All right, so let's go ahead and get at it. So I'm going to quit my kernel. Oops. Oh no, I pressed the wrong button. Okay, quit kernel. So let's go down. Let's go ahead. So we have metal, so 100 gigapascals. The length of the beam is equal to 24 centimeters. 24 times 10 to the minus 2. The width of our beam B is going to be equal to 32 millimeters, and the thickness, H, is equal to 0.48 minus 2 meters. And that is our width. Excellent. So our function is y times I times quadruple prime, and then we're going to do minus 30 times Dirac delta times x minus L divided by 5. And then we're going to do plus 2 times 10 to the 3 times Dirac delta. And we're going to apply that at x minus 5L divided by 6. So that's our function. Y prime is 0. Y is 0 is equal to this. Y double prime here is equal to 0. And then finally, we are going to do at x equals 0. And actually, we're going to go ahead and solve to our moment will just be equal to that. So we're going to do at y double prime, y times I times that. And we're going to have that set equal to minus 30 times L divided by 5 plus 2 times 10 to the 3 times 5L divided by 6. And there we go. So we have our value here. We have our boundary conditions. And let's go ahead and get started. Sorry, let's go ahead. I'm going to copy this solution here. Copy. I'm going to paste it in. There we go. Double check, make sure. Oops, I almost was guaranteed I was going to have an issue here because When we solve for the moment, we have to make this moment is going to be equal to, this is a minus. Because it's going to go like this, the moment will oppose, so I need to set this to minus. Actually, excuse me. Oh, excuse me. I'm sorry. It's been I did a long experiment the other day. Does that solution make sense? It does indeed, because we should be pushing up effectively there. All right. Oh, it's been a long day. So I'm going to find my maximum. Oh, I need sleep. You could set around 0.2. Let's see. It'll find the displacement. So there's my maximum displacement of my beam. Makes sense. That is in units of meters indeed. So there's my moment. There's my shear diagram, shear force diagram. And we can go ahead. What's the maximum? What are we asked to solve for? Maximum deflection. What about the maximum stress? So to maximum stress, I need to find the maximum of my moment. So I'm going to find the maximum here. Let's start 0.05, start the search. So this would be my maximum moment, right at 0, makes sense. There's no moment at the end there. Oops. Let's go ahead. So I'm just going to plug that into minus my moment times my h/2. And it is negative. Does that make sense? Yes, because we are going to be in basically that top of the beam is going to be in tension, or excuse me, in compression. So that's why the stress is negative. Told you, my brain isn't working. Let's see. Calculate the stress at the top surface of the beam. Let's see. Maximum stress we found. Calculate the stress at the top surface of the beam at halfway across the length of the beam. That is a very excellent question. So I'm going to do my moment slash dot x goes to L/2. And then I'll just calculate that moment. So that's positive. So my stress will be minus my moment times h/2 divided by I. So if I wanted to look at that, that would be my stress there. You see it's less than, or the magnitude is less than the maximum, which makes sense. Fantastic. Where's the shear force maximized? What is the value? So if I look at my shear, and we can find the maximum value of my shear force will be equal to this, minus 2,000. And it occurs all the way here. Fantastic. Below, I can see some dynamic mechanical testing curves of material A versus frequency, two other materials, B and C. B is a solid. C is viscoelastic that is more fluid than A. So, identify what symbols correspond to what. Relaxation frequencies, draw the curves of the material in figure 3. Rank the material's relaxation time and glass transition temperature. So, high frequencies, I must behave like a solid. So this is my G prime. At very, very, very low frequencies, I should flow. This is my G double prime. Excellent. So material B is a solid, meaning that and I'm going to call this is going to be I'm going to call this material B, G prime, and then my dash is going to be my G double prime. So if material B is a solid, it's always going to be solid, my G prime response, my storage modulus versus my loss modulus. My storage modulus must always be higher than my loss modulus here. And then for material C, we're told that it behaves like there's more fluid than A. So at this crossover point, it's behaving like a solid all the way across here. So something that's more fluid would have a crossover point, let's just say over here. And I'm going to say the same thing. This is my G prime. This is going to be my G double prime. So I'm going to have my G double prime going to be like this. And I'll have my solid look like this. Because here I'm only solid for that. Excellent. So identify the relaxation frequency. Blah, blah, blah. This is the relaxation frequency here for material A. This would be my relaxation frequency for basically material C. The relaxation frequency, so the relaxation time for B would be infinite. So the relaxation frequency is basically equal to 0 because it's inverse of the time. So a solid, it will basically take an infinite amount of time to relax back to that system. Ranking the relaxation frequency, so that'll be for the solid, it'll be 0. For the relaxation frequency for this, it'll be this, and nice. And draw the curves. What about the time? So again, B, the relaxation time will be infinite. A, the relaxation time for A, which is this, will be, because it's more solid, will be longer than that for material C. And that makes sense here because my relaxation frequency is smaller. So smaller relaxation frequency, larger relaxation time, larger relaxation frequency, smaller relaxation time. Makes sense. And glass transition temperature scales the exact same way. My TG of A will be greater than my TG of C. All makes sense. Fantastic. And the TG of B is basically infinite. And that's it for your problem 2. So see you in the next one. Thanks. Bye.